Today we are looking at the normal distribution, topic 17A, 17B, chapter 17 in your textbook, but today we're hoping to get through A and B, and I'm going to give you a bit of a preview on 17C as well. Have you ever seen, don't need a laptop, put it down, don't let it distract you, just focus on the screen. Have you ever seen this sort of distribution before? Yeah, great. What would you describe it as? Binomial, no. Bell curve, better. It's a bell curve distribution. Why do we say bell curve? It looks like a bell and then it has some curves on the outside. Crazy. Now, what happens with a normal distribution? The center of a normal distribution is the average. The middle of a normal distribution is the average result, and then it spreads out. Depending on the standard deviation is how spread out it's going to be. So there are lots and lots and lots of variables in the real world that we can model with a normal distribution. So this is intelligence. If you've done the year 10 psych course here, you would know that the average IQ is 100. The standard deviation for IQ is 15. So if we jump up one standard deviation, we're at 15. We jump up 2 standard deviations, we're at 130, 3 standard deviations, we're at 145, and apparently Einstein's IQ is somewhere around 160. So he was reported as 4 standard deviations larger than the mean. Adding from what we did last week with probability density functions, the area under this curve is equal to what? 1. Good. If this is the average right in the middle, what percentage of the graph is to the right of the average? 50. So 50% of the population is above the average. 50% of the population is below the average. And as you can see, less and less and less of the population is far above the average. Less and less and less is far below the average. All right. So 17A, normal distribution. How do normal distributions come about? We can start with a histogram here, which is height. Height is another variable. If we went out and we got the height of a bunch of people, if I got 10,000 adults, it might look like that. But if I went ahead and I got 100,000 adults, do you think it would stay as that same sort of almost rough bell curve shape? If I got more people, would we still roughly have that bell curve shape? Yeah, good. And if we got heaps more people, like 1 million adult males, it's going to get even closer and closer and closer to a smooth bell curve shape. Okay, so if we had an infinite population, it would get closer and closer to a smooth curve. This curve is called the normal curve. All right, and a normal distribution is appropriate to model lots of common continuous, only for continuous variables, continuous distributions. So what are some variables that we could model with a normal distribution, where we have most people fall on the average, and then there are a few people above average and a few people below average? What do we got? Weight, excellent. There would be an average weight, maybe depending on how old you are, probably would look different for males and females. Weight, good. What else? Height, good. Any other continuous variables we can think of? Age. Okay, when you think about the average age of the population, it probably is, where are most people going to be? Where's the maximum? Do you think it's going to be normally distributed? Do we have a lot more like 50-year-olds and then very few 100-year-olds and very few infants? Age probably is not going to be normally distributed, because I don't think we would have a greater number of 50-year-olds, but I could be proven wrong on that. It can't be normally distributed. Lovely. Okay, so some examples might be weight, IQ, hand span, height, whatever. We've talked about a lot of those, so that's good. Hand span, how much are hand spans? All right, who's scared now? Yep. Integrate it, go. Just kidding. All right, realistically, I would like you to write this function down. This is the normal distribution function. Write it down, process it, have a look at it. This is the probability density function for a variable that follows a normal distribution. All right, so that is your formula for a normal distribution function. Do we recognize any symbols in that function? Pi. Good. Pi, in this case, pi still represents roughly 3.14. That's good. What else? Mu. What does mu represent? The mean. Can you picture where the mean is on your bell curve? The middle, the maximum. Good. Do we recognize any other symbols? Sigma. Sigma is that lowercase sigma there. What does that represent? Standard deviation, which is an indication of how spread out your data is. X we recognize. E we should recognize. That's like pi. It's an irrational constant, roughly 2.7. All right. So some of those letters have not changed at all, and we have seen them before. Okay, a normal distribution. Do you remember this notation that we looked at last week for binomials? If a variable was distributed binomially, we would write what letter here? B. And what letter would we write here? N, representing number of trials, super job. What would we write here? P, representing probability of success. Now, we are not talking about a fixed number of trials today. We are not talking about a fixed probability of success. Today, we're talking about a normal distribution, which is for continuous random variables. So if we have a normally distributed variable, we say it's distributed normally with the parameters mu, and sigma squared. What is sigma squared? If sigma is standard deviation, wow, you guys are amazing. Variance. Can you please highlight that squared? The biggest mistake I see is that we give you guys X distributed normally, the mean is 5, and then we write sigma squared equals 4. And so many of you go into your calculator, when it asks you for sigma, you type in 4. What should you type in? 2, the square root of it, okay? So please just be careful with that. It is sigma squared. Now, let me just show you what happens to the graph. We know that our graph is symmetrical. We know that it's bell-shaped. We know that it's centered around the mean. Let me just show you what happens to that graph when we adjust the mean and the standard deviation. The mean is this middle point. So if I adjust the mean, which is currently set at 0, what do you think is going to happen if I change the mean to +1? Move. Can we be specific? Shift. Can we be like more precise with our terminology that we've taught you? A translation. Good. Vertical, horizontal. Horizontal, good. So if I go M is 1, it's going to shift to the right to 1, 2, there we go. If I shift M to the left, there we go. So if you adjust the mean, it's going to move left and right. Standard deviation is the spread. If I increase my standard deviation, am I increasing the spread or decreasing the spread? Increasing the spread. Okay, if you increase the spread, what is that going to look like for our bell curve? Bigger, taller, wider, shorter, shorter and wider, because here we go. So I'll increase it. There we go. It's flattening out. what does the area under that curve have to equal? And it does not change. It needs to stay as 1. So if I'm going to make it wider, I have to make a dilation parallel to the y-axis as well as the x-axis, which, if you look at that formula, you can sort of see it happening. Where it happens, sorry, let's just get that PowerPoint back up. Have a look at that formula you just wrote down and see if you can identify where that dilation parallel to the x-axis and the y-axis might be happening. And the horizontal translation. So the horizontal translation, easy enough to see. We can see that take away C there, that minus C. That's your horizontal translation. Can we see our A value anywhere in here? A value in our A, B, C, and D. Which sigma is it? Is it this sigma out the front or is it the sigma under the X? Out the front, that's our A value. And normally we multiply the function, we dilate it parallel to Y by a factor of A, but you can see it's 1 over sigma, so it's going to be dilated parallel to Y by a factor of 1 on sigma. So if sigma's 2, it's going to be squished down by a half. And then you can see your B value is in here. Normally B, what happens with B normally? Dilate by a factor of 1 on B, excellent. But can you see that it's being divided by B? So if you're dilating by 1 on B, but B is under 1, it's actually doubly cancelled and you're actually going to multiply by B. It's confusing. All right, good. Don't have to stress about that too much. Okay, quick sketch. Can you please sketch for me? Just a normal distribution, mean of 0, please, and standard deviation of 1. Give me a rough sketch of that. Mean of 0, standard deviation of 1. Just your normal distribution. A typical normal distribution, mean of 0, standard deviation of 1. On that same set of axes, now, I want you to try and put a graph that has a mean of 1 and a standard deviation of 1. So one thing's going to change, but the other should not. Okay, so for part A, your sketch should look something like this. We have got in blue here, that is your standard normal distribution, which is centered at 0 with a standard deviation of 1. And then part A asks for a mean of 1. That means we shift the whole graph, we translate it to the right, and we center that graph on 1, but the standard deviation, the spread, should be the same. Hands up if you roughly had that. Okay, well done. And then the second one, how is the second one going to look different? It's going to be flatter, it's going to be shifted to the right, and a little bit flatter. Half the height of your original. And double as and out wide. Congratulations, you finished 17. Next one. Yes. All right. Have a 5-second stand up and stretch. I'm going to do the roll. 17B now. Standardization. If X is a continuous random variable that has a normal distribution with mean of mu and variance of sigma squared, then we write X is distributed normally, square brackets, or round brackets actually is fine, mu comma sigma squared. Can you please write down the standard default setting for a normal distribution using that notation? The mean is 0, good. That is just the default setup for a normal distribution. Yeah, mean is 0, standard deviation is 1. It's based off a Z distribution, which we'll get onto a little bit tomorrow. Have we heard Z scores? No? We'll leave Z out of it. Okay. So there is your normal distribution. Now, has anybody heard anything to do with the amount, the percentage of people that fall one standard deviation either side of the mean? Or the percentage of people that fall two standard deviations? Have we heard anything about some magical percentages that typically work for normal distribution? Inner quartile range is slightly different, but you're kind of there. What percentages have we heard? 70 is close. Higher. Lower. Lower. Higher. Higher. 68. One standard deviation either side, above and below. So from -1 to +1 for your Z distribution. 68% of results will be in that, which you can see on the graph here. If I go between one standard deviation up and below, 68%, almost 70% of the shaded region is in that area there. 68% is your first magical percentage. So it's 68.3% if you're interested. Two standard deviations now. Have a guess for me. So that's how we write it there, guys. Mu minus one standard deviation. So the mean minus one standard deviation all the way up to the mean plus one standard deviation. That area under the curve is 68% of the data. Now, two standard deviations. Excuse me. 93. Higher. Higher. Lower. Lower. 95. Have a look now at this graph. If I go back two standard deviations, how would you describe this point here in terms of sigmas and mu's? Mu minus 2 sigma. Beautiful, Calissa. Mu minus 2 sigma. That is the mean minus 2 standard deviations. If I'm on my Z distribution, what point is that? The mean 0 minus 2 standard deviations. -2. Yeah, with the standard deviations 1, isn't it? So -2. All right, so then we go from there all the way up to here, and you can see that it's most of the data. In fact, it is 95% of the data, 95.4% of the data. Most people fall within two standard deviations of the mean. So if you look at IQ, IQ is normally distributed with a mean of 100 and a standard deviation of 15. So you could say with some confidence that 95% of people in the population fall between what two values of intelligence? 100 is the mean, standard deviation is 15. 70 and 130. And in fact, one of their tests for an intellectual impairment, to be classified as somebody with an intellectual impairment, is to be less than that 70 cutoff. To be in the, now let's think about it. This is 95%. It is symmetrical. So what percent is hanging out here? 2.5. Well done. There's 5% on either side. Split up is 2.5. So to be classified with an intellectual impairment, one of the categories is to have an IQ less than 70. The lower 2.5%. All right, 3 standard deviations. What percentage of the data do you think goes between mu minus 3 sigma all the way up to mu plus 3 sigma? 99.7. You cannot round to 100. Imagine Einstein, for example. He was 4 standard deviations above the mean. There are always outliers that don't fit in those 3 standard deviations either side of the mean. So please don't round and say 100% of people are there. Okay, So that is something that is fair game for you to have to remember. 68%, 95%, 99.7%. We will not be giving you those percentages. You have to know them. 68, 95, 99.7. What can you tell me the percentage from here, one standard deviation, up to the mean? What would that look like? 34%. Good, because it's half of 68. Those are the types of questions we will have to answer. Okay, so you've got 2.5%, 13.5. I would not bother remembering all of these. I would just remember 68, 95, 99.7. So all this is saying in really fancy maths, if you want to go and press someone, you could say, hey, the area under the probability density function for a normal distribution integrated with respect to x between the lower bound of mu minus sigma up to the upper bound of mu plus sigma equals 0.68. Pull that one out at your next party and people will love you. Yep. Alrighty. I've been doing a lot of talking. Sam, can you read this question for me, please? Louder so the other half can hear you. Lovely. Right, you shouldn't need to do any work. Maddie, what's the answer for what percentage lies within one standard deviation? As a percentage? 68%. Alex, what percent lies within two standard deviations? 95. And Alina, what percent is within three standard deviations? 99.7. Done. Finished. Well done. Alrighty, someone from this side. Rach, give it a read, please. Right, what's our answer? What percentage are more than two standard deviations above or below? 5? Yep, there's going to be 2.5% above, 2.5% below. Okay, your turn. Off you go, please. A bit trickier, but not too hard. My advice to you for this question is to start with a normal distribution. Maisie, what's one thing I could label on my normal distribution? The mean is 95. So I put my mean in. There it is, 95. Ali, what else could I put on my normal distribution? One standard deviation. Okay, so how much one standard deviation above the mean is going to be what value? 103, lovely. So you label in 103 there. Jamie, what's one standard deviation below going to be? 87, lovely. So we put in 87. And two standard deviations above the mean. What are we looking at? 111. All we are doing, guys, is adding sigma, which in this case is 8, to our results. Kaja, what goes here to the left? There's 87 there, and now we're going to go one standard deviation to the left further. 79, perfect, well done. And then we go up to here. Maisie, what have we got up here? Sorry, Alex Mays. Sorry. 119, perfect, sorry. Yeah. And J10, what about all the way down to the left here? 71. Excellent. Now we have sufficient information to find the percentage of people between 87 and 103. So between 87 and 103, what's our answer? 68%. Good, because that's one standard deviation above or below. Between 103 and 111, 13.5%. Between 87 and 111, 81.5, I agree. That's adding your 68% to your 13.5%. And then the last one says, find the value of K such that approximately 16% of the chest measurements are below that number. What's our number for K? 87, that's it. Well done. Okay. So, one standard deviation either side is what percentage? 68. Two standard deviations either side is 95. Three standard deviations, 99.7. Now, what if I asked you something like, find the percentage that fall between 90 and 100? 90 and 100. Any takers? Split the 34? That's what's going to be happening, but how do we mathematically figure out where it gets split? Formula? Okay, so the plan is we are going to integrate between 90 and 100 and then do that maths? No, too much work, too much work. So we are going to use our calculators, which is why I asked you to have your calculators today. Alrighty, do we all have our calculators with us? Yep. Does anyone not have one? I've got two spares up here. I need you to have one. Anyone else not have one? Don't you need a spare? Alrighty. Think about where we went last time we used some sort of probability distribution. Where did we go? Stat mode, good. Hop across to stat mode, please. Then where did we go? Distribution, F5. And last lesson we used F5, or last time we used F5, which was binomial. What do you think we're going to use this time? Oh, F1. There it is. Okay. Similar-ish idea to last time, except it doesn't make sense with a continuous random variable to say the probability that's equal to something, so we won't be using NPD, we'll be using NCD because it's between values, so NCD. All right. This calculator is asking, do you want it in list mode or variable mode? Do you want it in variable mode? This question says, X is distributed normally. This 10 here, Josh, what does that 10 represent? Okay, expected value, a synonym for expected value, Lara. Expected value is the E of X, yes, but what is it? Mean. Mean. It's 0 in the Z distribution, but not for this one. So that's your mean or your mu. Now, this question has been kind to you and it has reminded you that we do mu comma sigma squared. It has told you 2.3 squared, so it's told you what sigma is. So what we are going to put in, we want to find the probability that it's between 8 and 11. What do you think our lower bound is going to be? 8. What's our upper bound going to be? 11. What's sigma? 2.3, that's the other mistake people make. They type in mu there and sigma on the next line because that's how it comes in your brackets. Mu is 10, execute, and the answer is 0.47. Now, right now, I have done nothing on my page, and I have an answer. Do you think that's going to be good enough for your exam to just come in and write 0.47? No. Okay. Let me show you what we would like, please. And it's not just what we would like, but it's what you actually need to do. So, for all of these questions, you will need two things. You will need some sort of diagram. And then you will be able to give some probability, and we normally express probability to how many decimal places? 4 decimal places is correct. Okay, so what sort of diagram do you think I'm going to be drawing? A bell curve, lovely. So you draw a bell curve. It doesn't have to be perfect, but you draw some sort of bell curve. On that bell curve, what can I label? Mean, lovely. Mean is there, 10. Now, 8, is that to the left of the mean or the right? There it is. 8 is there. 11 is closer. It's there. And you need to communicate to the marker that this is what you are calculating. You are calculating the probability, which is the area under the probability density function, between 8 and 11. So you communicate some sort of diagram like that, and then you say, using GDC probability that x is greater than or equal to 8 but less than or equal to 11 is 0.4759. These questions are a gift. If they come up in your exam, they are a gift. Okay, let me show you B because it looks a little bit different. Can you actually sketch a diagram for me for B? And then I'll show you what happens on our calculator. You can have a crack if you want. All right, guys. This one, your mean and standard deviation stay the same, so we'll leave that. But we need to change our lower and our upper values. What's the easy one out of those two to change? Upper is 12. Lower, now think about what happens with that bell curve. There can be extreme outliers. So your lower bound, if we're saying less than 12, your lower bound is not 0. So if it's ever something like this, less than or greater than, you put in an extreme value, negative 1,000. That will cover your outliers. That's crazy. I always just say negative 1,000 if it's less than and positive 1,000 if it's greater than, as your lower or upper respectively. It might change the probability, probably not. Like what I did there? All right, so you press execute and you get 8.8078. Now, Josh has just showed me something pretty cool, but I can't see it on my calculator. So, pardon? Okay, if you go back to this page and you scroll to the bottom, there it was. Scroll all the way to the bottom where execute is. Can we see execute? Oh my goodness, draw pops up and you copy that diagram in your exam. Well done, Josh, good find. I love it. That's awesome. All right, what are we putting in for our lower and upper bound for the next one? X has to be greater than 9. Upper 1,000, I like it. Lower 9, easy. And we can go all the way down. Press draw if you want, and it will also execute, and you get a probability of 0.6681. That diagram needs to be in your answers. Your calculator does it for you, so no excuses. Okay, you guys have been super today. I'm just going to give you a couple questions for the last 2 minutes, but that's about as tricky as it gets. Okay, there are 2 questions on the board. I'm going to come around. I want to see exam style setting out for those questions, please. Okay, you need your diagram. It should look, you should be defining what your variable is. So you have X is distributed normally with mu comma sigma squared. Then we have our diagram where we label the area we are calculating. We say using GDC, and then we clearly define the probability that we are looking at. Easy communication marks to lose, so please take some note.